Okay, so here we are with lesson 1.3, I'm sorry, 3.3. We're going to be doing implicit differentiation. And all the derivatives that we have done so far have been examples of explicit equations. For example, y equals that, y equals that, and y equals that. Now, the words I'm going to use here and highlight right here are very important, that those functions all explicitly express y in terms of x. Now, we have used other variables in class, such as t or theta, and if we had those variables in our equations, we would say that it expresses explicitly that function in terms of t or in terms of theta. So x just happens to be the variable that we're talking about right now. But in this lesson, we're going to be working with implicit equations where the relationship between x and y is only implied. We have not solved for y here. We actually cannot solve for y with that one. And this one, we have not solved for y. So specifically, we recognize that this one right here, I'm pretty sure, is the equation of a circle. That one is what? The function 1 over x. So we recognize those, right? If we solve them for y, we totally know how to do that using normal algebraic operations. This one, on the other hand, cannot be factored, right? I can't factor all the y's out and create an equation where y explicitly equals something. So that's when we have to take a look at our method of finding a derivative. And you might even be wondering about that equation. Let's take a look at Desmos. I've graphed it. You maybe didn't even know that Desmos could graph it, but it can. It's very clever that way. And so when I want to think about finding the derivative, I'm looking to find the rate of change at a particular point. Well, what you'll notice about this is that, say, for example, when x equals 5, somewhere over here, when x equals 5, I'm sure that I could construct a tangent line at that spot, right? To express that derivative for me, that rate of change over here. But I also have another moment where x is equal to 5. And so what we'll find with these is occasionally we'll have to decide what y value are we looking at. Am I looking to find the tangent up here, or am I looking to find that tangent down there? But in any case, I just wanted to make sure that even though it's not a function, right, that line fails the vertical line test, it is still something that I can find the derivative of. And so there's a process to this where we differentiate both sides with respect to x. And he's saying that you want to remember the y prime, which is the chain rule factor for any term involving y. And I wanted to mention that I actually do not use y primes. Personally, I really prefer the Leibnitz notation of dy dx. I'll show you an example, a few examples with my dy dx's and why I use them, and then you will be able to make a decision later on if you just want to use those y primes, okay? But we're going to have to we're going to have to collect all of those terms onto one side of the equation, and then we're going to have to factor them, and we're going to have to divide to solve for that. The thing that we're looking for is actually going to be that y prime. That will be our derivative that we can then use in order to find the equation of a tangent line or the slope of a tangent line, the value of the derivative at a particular point. So we have these warm-up examples, and again, I would just really quickly, I want to say that the reason that I like the Leibniz notation is because it lends itself very well. When I say that I want to find the derivative of the y function, then you've seen me do this notation where I say I want to take the derivative of something. Well, if I have y equaling, I don't know, 6x, and then I say I want to take the derivative of that, then it would look like this. And it's like I'm applying the derivative concept to each side, which is how I end up with d dx of y is going to be a dy dx. And then d dx of 6x, well, please take the derivative of 6x. You've been seeing me use this notation where I say to you, please take that derivative. And remember that that's what that means. And so when I do take the derivative, I get a dy dx, and that equals 6. All right? So there you go. Oh, silly me. So let me take a moment and explain why it is that I like the Leibnitz notation, okay? Specifically, I think it helps when we're doing these introduction problems for me to say that if I'm asking you to take the derivative of the function y equals x, then it's like I'm doing this. I'm saying, hey, can you take the derivative of that? And by the way, applying that d dx concept to y would mean that what I end up with is a dy dx, okay? And then in the rest of it on the other side, because it's like I'm distributing it, right? I would say, hey, can you please take the derivative of x? And you're like, oh, yeah, okay, I definitely can take the derivative of x. Well, what do you end up getting then? Ready? What I end up getting is dy dx equals the derivative of x is a 1. But mentally, I'm going to tell you that I use this notation where I say that dx dx is a thing that I've done. I have taken the derivative of x. And I do this as a reminder when I'm working with variables that are, all nestled up inside of an equation together. When I take the derivative of x, it feels natural. When I take the derivative of y, it won't feel natural at the beginning, and I might forget to write down that dy dx when I've taken its derivative. So here I'm going to say the derivative of an x is literally the same thing as the derivative of 1x, which means my derivative is 1. But I will write down this extra step, dx dx, just to remind myself that I have taken that derivative. And eventually you're going to tell me, many students do, I'm not doing that, Ms. Shatra. I don't need to do that. But there are students who are like me, where we forget to take the derivative of each piece. And so when we do the dx dx, it just helps to remind us. And here's the magical power of that dx dx. Guess what? The change in x over the change in x. What if the change in x was, say, 3? Well, then I would have 3 over 3. What is 3 over 3 equal to? It is equal to 1. So I take that derivative, and then I write down that I took the derivative, and then I actually just cross it out later. And I'm going to tell you that my final answer here is just dy dx equals 1. And you're like, ooh, why would I do those extra steps? Here, just let's practice it for a bit, and then we'll see whether or not you agree with me and whether or not you choose to keep using this notation. So y equals x squared. I'm going to say, hey, the derivative of this is dy dx because why? Why is that the derivative? Well, if I take the derivative of y, if I take the derivative of 1y, well, then I should get a 1. And so there is technically a hidden invisible 1 here. And when I take that derivative of y, I always want to remind myself to write down the dy dx, because my goal is to solve for that dy dx, okay? So what about over here, when I take the derivative of x squared, I'm going to get 2x, but again, I'll mention I always just write down a dx dx. This part disappears. This part I didn't need. So ready? Dy dx equals 2x. You're like, I could have done that already. I totally know how to take the derivative of x squared. I know, but we're just practicing the process for a little while, okay? Just so that we feel like we know. And I should start using greens. It's that time of year. So how do I take the derivative of number 3? I'm going to get a dy dx because the derivative of y is 1. And so whenever you take the derivative of y, you also write down the dy dx. And then over here, I'm going to say that I have something on the outside, and it's that 2. And then I have something on the inside, which is the 2x minus the 1. And the power on the outside is reduced, remember? Then on the inside, I'm trying to use the chain rule here. I want to remember, take the derivative of this 2x minus 1. And it's when I'm doing this that I realize I'm going to take the derivative of x. So the derivative of this is going to be, ready? It's going to be a 2 and a dx dx. And then I'm going to bring down the rest of the equation. So I have dy dx equals 2 times 2x minus 1. And yes, I know you're mad at me already for writing down the dx dx because you knew how to take the derivative of this anyways. And why am I making it so complicated? Ready? Dy dx equals That's 2 times 2 is 4, and 4 times 2x is 8x, and 4 times negative 1 is a negative 4. So that is going to be my answer on that. So hopefully you're starting to feel the pattern, and you're going to see the reasoning behind this kind of work as we move forward. When I do number 4, I think, just to please you, I will go ahead and use that y prime notation that you know and love, okay? Let's try one your way, just one time. So the derivative of y is y prime, and the derivative of something that has been squared, I will need to bring the 2 out in front, and I will need to reduce that power by 1. On the inside, I should still have that f of x. But don't forget that we still want to take the derivative of that f of x. And in my mind, I'm already doing it. Hold on there. Okay, so y prime really equals, ready, what is the derivative of f of x? Well, it's f prime of x. So I should have a 2, and I should have an f prime of x, and I should have the original of the interior function, and that interior piece would be f of x. And that is my answer. Okay? So you're like, well, that was a lot easier. Why don't we just do it that way? Okay, fine. If you want to start doing it that way, go ahead, and you can actually pause, and I believe that you could find the derivative of number 5 without me. So go ahead and give it a shot. All right, so we're back, and you were saying that you took the derivative of 5, and I just wanted to show my method for it, okay? So let's see if we both ended up with the correct answer. Ready? The derivative of x is 1 dx dx, because I always write down when I take the derivative of x. And then here, I want to take the derivative of y squared, and I should get a 2y. But my memory is very strong that I always write down either a dx dx or I write down a dy dx every time I take the derivative. Did you remember that? So if you did actually come up with a y prime somewhere, then you've done it right. But if you haven't come up with a y prime, then you might want to use my method, okay? And by the way, I have kind of been taught to always solve for dy dx. Technically, if what you wrote was this, 1 equals 2y times y prime, then you are correct, and you don't actually have to solve for anything. But that's just my habit to do it. So I'm going to say then that dy dx can be solved for, and the way that I would solve for it is by dividing by 2y on both sides. And I would then say that dy dx equals 1 over 2y. And you also could make that step over here. You could do the division by 2y, and you would get y prime equals 1 over 2y. And are you allowed to leave it like that? Yes, you are. So all of these answers are correct. And I pick your favorite and go forth from there. All right. So that was number 5, and we've practiced sort of the methodology of it and the reasoning behind it. And so I'm happy now to actually go in here and do some examples. Example number 1 says find y prime, and I will mention you could see this where it says find y prime, or you could see it say find dy dx. And I'm going to use my dy dx's, okay? Here we go. So given that x squared, if I want to take the derivative of it, I'm going to get 2x dx dx, just to remind myself that that's what I'm looking for. When I take the derivative of negative 2y cubed, I'm going to get a negative 6y squared, and here's my dy dx, and eventually I want to solve for that. And then I have the derivative of 3x is going to be a 3, and here's my dx dx. And don't forget the derivative of 6 is just a flat, straight 0. The derivative of a constant is a 0, and whenever I take the derivative of a constant, I don't have to write down any kind of dy dx or dx dx business. All right, so now I go through, and I know this is annoying for some of you, but for some of us, it's a lifesaver that we wrote down dx over dx, reminded us to write down this very important dy dx. This is the thing that we actually want to solve for. So what I'm saying is that I'm going to minus 2x from both sides, And I'm going to minus 3 from both sides. And it looks like this, minus 2x and minus 3. And what do I end up with? Well, what I end up with is a 6y squared, and it's negative. And there's my dy dx. And then I have a negative 2x minus 3. And then dy dx can be isolated by dividing by negative 6y, dividing by negative 6y, and I'm not even going to write that. I'm just going to write the next step. Ready? Dy dx equals negative 2x minus 3 divided by negative 6y. And you can leave it like that. Or a lot of kids, you know, we don't like a whole bunch of negative things in there. So we maybe would factor out some negative ones. Factor out some negative ones. This 2x plus 3 is now on the inside, and this negative 6y squared is got a negative 1 out in front and is positive 6y squared. Those guys factor out, and so my real final answer will be dy dx equals 2x plus 3 over 6y squared. Do you have to factor out the negatives? No, you don't, unless it's multiple choice. If it's a multiple choice question, I guarantee you that the College Board would factor out all of those negatives in your multiple choice answers, okay? For number 2, it says find the slope of the line that is tangent to and normal to this graph. And I don't know why my lecture notes have a typo in them. I'm looking at the answer key. I could see clearly that Mr. Taylor is wanting us to go over the idea of the normal, just in case you've forgotten it. So why don't we go ahead and do that? All right. And I always need a little bit more room. So when I'm taking the derivative of x squared, I'm going to get a 2x dx. 2x dx dx. And when I take the derivative of 4y squared, I'm going to get an 8y dy dx, and I'm not going to forget to write that dy dx down. The derivative of 25 is 0. So I'm well on my way to finding my derivative. I know that that part doesn't matter, and by the way, I want a minus 2x from both sides. And so I'm going to end up with this new equation, 8y dy dx equals negative 2x, and I want to divide by that 8y, and I want to divide by that 8y. I'm not going to write that down just because of space. Dy dx really equals negative 2x over 8y, and this can be reduced, simplified into a negative x over 4y. So how do I go about finding those slopes? Well, this is my derivative, which is the same thing as the slope, right? So when I want to evaluate this, by the way, you can write it like this. He's given us an x and he's given us a y. And that was actually really kind of him. And he kind of had to do that. He had to tell us which y we wanted to find it at, right? Because again, this is the equation of a circle. And so there'll be a top part and a bottom part where y equals two different numbers. And so he told us we wanted to know what happens when x is 3 and specifically when y is 2, because that, instead of the other version, likely where y equals negative 2. So if we're going to do that, then let's actually have some introduction of some notation, which I particularly love, which is where I say I'm finding dy dx and I'm evaluating it at 3, 2. And so this little piece of notation here is I just like it. It looks really good to me, that it mentions, hey, which values am I plugging in? So I will get a negative x over 4y, and the x is a 3 and the y is a 2. And so what I end up with is negative 3 over 8. And that is going to be the slope of the tangent. And so if you're doing the AP exam, right over here I said m. It might have been better if I said m of the tangent. Whoops, not the tangent. The tangent with an n there. All right, so m, this is the slope of my tangent. And by the way, the graders do recognize that notation. If you forget that notation, you can actually just write the word tangent, slope of the tangent. You can write a sentence, it's fine. How do I find that normal? Well, the slope of the normal, if you want to continue with this notation, would be the opposite reciprocal. So the opposite means that it's going to be positive, and the reciprocal means that it will be 8 over 3. So these are the two pieces. that we were looking for in order to solve this problem. So have you gotten used to the idea of taking the derivative, and how do you want to go about finding that derivative? If you want to use y primes, it's fine. Feel free. I'll mention that when you're successful, you know it, okay? But for the rest, and it turns out you don't even need to see examples with the y primes, because if you're good at it, you're just naturally good at it. But the rest of us that are struggling with just how to take the derivative of each piece, we need these dx's. So the derivative of x cubed is going to be 3x d squared dx. The derivative of negative 2xy. Uh-oh. Wait a minute. What? I have a product there. How do I go about finding the derivative of a product when one of the functions isn't even x? All right. So here's one that I just kind of recommend that you memorize. And I will mention the way to memorize this is actually to just do it several times. So here's me saying, hey, can you please take the derivative of x times y? And yay, it's all holiday. And here we go. So what will that end up being? When I have an x, I will take the derivative by saying I have a 1 dx. Remember, we are looking for dy dx somewhere. So we need to make sure that when we take the derivative of something that we get that dy dx. So here's my y, and when I take the derivative of it, I get 1, and here's my dy dx. Okay, do you see now why I insist on using this dx notation and the dy dx notation? Is so that I will never forget that to be able to find that y prime. That's the thing that I'm solving for. So here then, the product rule is something times something plus something times something, and you want to memorize the final step, not the middle step. The middle step looks kind of ugly. This is going to be x, and this is going to be dy dx, right? 1 times dy dx is the same thing as dy dx. This is going to be dx. I don't write that down. This is just a 1. Okay, again, very boring. And what is it multiplied by? Just a y. So when you memorize this, this is what you want to memorize. Ready? X dy dx plus y. The derivative of the product x times y is x times dy dx plus y. All right, so I'm going to use this now. And I'm going to use it right over here on problem number 3. So what was our derivative? Well, if you haven't done it, a bunch of times, and you maybe don't have it memorized, it is going to be, ready, x dy dx plus y. Okay? Now, having done that, I will finish up the rest of the problem, and I'll say that I have y cubed, and I'm going to take the derivative of that, and I'm going to get 3y squared dy dx, and that equals, ready, what's the derivative of 5x? It's 5 dx dx. Okay, so I realized I was writing, moving it over, so here we go. When I get interrupted, which, by the way, you may have noticed that I just got interrupted, the fact that I wrote the dx's is actually really helpful to me, because it lets me know, hey, I'm done taking the derivative. I'm not going to accidentally take the derivative again, which is another mistake that I do see students making, okay? The other thing is, by having this little piece in black be memorized, anytime there's just a constant thrown out in front, I can substitute in the thing that I have memorized and finish up the problem, I think, relatively quickly, okay? So now I'm going to say that I have a 3x squared minus a 2x dy dx minus a 2y plus a 3y squared dy dx. I can write that better. Dy dx. And that will equal 5. Now what I want to do is I want to try to isolate my dy dx's, and they're so important to me, I'm just going to highlight them. There's one and there's another. And so the terms that are kind of in my way is this 3x squared. So I'm going to minus the 3x squared from both sides. and I have a negative 2y, so I'm going to add 2y to both sides. And so when I am done with that, I end up with a negative 2x dy dx plus a 3y squared dy dx, and that will equal 5 minus 3x squared plus 2y. And certain students will start thinking to themselves, this is really boring, and do I have to show all of this work? And the answer is no, you do not have to show all of that work, but you do have to be extremely careful. So when you get bored, please make sure that you are moderating your thoughts to a point where you are being very careful about signs and about what you're moving before you just sort of jump to the answer. But I do believe in you. I know you can eventually get to this answer, where I'm going to factor out this negative 2x, and I'm going to factor out that positive 3y squared, and we know that we're going to end up dividing by it, and so what we'll get is a dy dx, and it's going to be equal to 5 minus 3x squared plus 2y, and it is going to be over that negative 2x plus 3y squared. Now, just eyeballing this one makes it really obvious to me that we cannot simplify that. We cannot factor anything. And we were just asked to find that dy dx. And so it turns out I don't have to factor anything, and I don't have to worry about that. The graders will have all of these different algebraic versions of it. Even if you could factor, they will actually have the answer without factoring so that they can, match and give you your points. Okay, so that's a check mark. Boom. I'm going to get my points because I found my dy dx. How do I find it at the point 1, 2? Well, again, you notice that he gave us the y. So that was really kind of him, because there's probably 2 places, or at least 2 places, where y equals something and when x equals 1. So in this case, then, I can say my dy dx is going to have a 1 and a 2 be thrown into it. And that means that I have 5 minus 3 times 1 being squared plus 2 times 2, where y equaled that 2. And then I have a negative 2 times x when x is 1, and plus a 3, and y is a 2, and it should be squared. And when you simplify all of this out, what you will end up with is 3 over 5. And I leave the the arithmetic to you. So now that we've done number 3, we realize we might need extra paper. These problems, these implicit differentiation problems, we definitely might need some paper. It just turns out that they're very big. And so I will also say, ooh, I know you're jealous that I can shrink stuff. I know you're jealous. For this next one, it says, given that x squared plus y squared equals 3, please find y double prime in terms of y. And that means the second derivative, right? So I like this notation. This is the moment where if you want to try this, go ahead and pause me and try it your way with y primes instead of dy dx's. And when you're using those y primes, you don't write anything when you do the derivative of x, because remember that dx is equal to 1. Then when you're done pausing, you come back and you can check my answer here, okay? So I want to say, and this is a perfect moment for me to say it, that the notation for taking the second derivative actually has a place in my heart, very special place in my heart. If I take the first derivative, d dx of y, I should get dy dx, and I already showed you how I get that. But if I take the derivative again, d dx of dy dx, it really works like this. The d's get squared because there's a derivative d and a derivative d up here, and I square those. The dx's get squared together, so I see a dx squared. That's where that notation comes from. I'd already introduced to you that this thing means the second derivative. but you had already forgotten. And that's okay because it looks weird, right? But now that you've seen me do implicit notation and you've seen the Leibnitz notation, you could see why I'm going for it. By the way, those of you that love this y prime business, this is Lagrange. And the Lagrange notation is very popular because it's the most lazy version of it. But we will mention that Lagrange and Leibniz notations. Leibniz came first, and he was actually a master of notation and is one of the fundamental discoverers of calculus that nobody can dispute over and over and over again because he perfected notation. All right, the notation that Newton created is still hardly used at all except by physicists. So the fact that Newton and Lagrange were both Newton and Leibniz were both contemporary, they were colleagues from across the countries, one of them in two different countries. It's interesting, but Leibniz's notation has endured because of its usefulness and the fact that it logistically it makes sense. Okay, so when I go ahead and work out this problem, then I clearly am going to need a little extra space. Okay, so here I'm going to give myself some room and I'm going to attempt to work this problem out then with my Leibniz notation. So finding the derivative of x squared plus y squared equals 3, I will say then that I have a 2x dx dx. I have a 2y dy dx. You see how it just feels natural? And then the derivative of 3 is 0. I cross that out. Again, it feels really natural. I'm going to minus 2x from both sides. And I'm going to say that I have a 2y dy dx, and that equals a negative 2x. I want to divide by that 2y. I want to divide by that 2y. I don't write that down just in terms of saving space and time. Dy dx equals a negative 2x over a 2y, and I can reduce that to a negative x over y. Wow, that was really easy. Okay. So that's my first derivative, negative x over y. And for those of you that are doing it with the y prime notation, you can then say that you have y prime equaling negative x over y. And Mr. Taylor picked this example on purpose because he wants you to learn how to do the quotient rule with two functions that don't use the same variable. So again, this might be one that you want to memorize, but obviously you will need to be able to come up with an answer to this just basically all the time. And I myself, I'm not even going to bother with a negative version of it. I'm going to throw my whole answer in and then make it negative when I'm done at the end. So what I want to do right now is just finding the derivative d dx of x over y, because negatives mess me up and I don't need them in my life, all right? So if I take the derivative of x, I will get a 1 dx dx, which I can cross out. And when I take the derivative of y, I get 1 dy dx. And so my derivative of these two things, remember how the quotient rule works, something times something minus something times something over something being squared. And what is in the bottom is supposed to be the original denominator, and that is squared. And it also goes up here on top. And so if I've done y, then I need to multiply it by that, and then I will need to multiply this times this. So this will be where I put my dy dx, and this will be where I put my x, and this will be where I put my 1. And I believe I can simplify that and make it look just a little bit neater. And I will do so when I plug it in right here. Ready? My dy dx is really a d squared y over dx squared. That's my second derivative. I'm going from here to here. Say that I have the negative version of y times 1 is y, and dy dx times x is really x dy dx. And I'm throwing that all over, ready, y being squared. And can you leave this answer like this? Indeed, you can if you want to. All right. Now, having said that, though, I do recall from my days with my calculus teacher where she said that if you can simplify anything out, sometimes miracles happen and it makes it look nicer, okay? So I would say that if we know that dy dx is negative x over y, it is probably true that we can make this look a little bit neater, all right? So how would that look then? Well, dy dx is negative x over y, so I want to throw that in. And I will say now that I have a negative y plus, well, so, no, I don't want to distribute the negative while I'm also going to plug in something that is negative. That messes me up. X times, this is negative x over y, and then I want to have my y squared all on bottom, and I will work this out to be a negative y, and here this is x squared and it's going to be positive, and then I have to make it negative anyway, so this will be a negative x squared over y, and the whole thing is over my y squared. And do you remember how to clear a fraction of nested fractions? You might not, so I'm going to go slow. And if you do know how to do it, then why don't you pause and try it, and you'll get to the same answer as I do, but potentially with fewer steps. So if I have a denominator of y, then what I want to do is I want to multiply everything by y. I want to multiply this whole expression here by y, and I want to multiply that whole expression there by y. And then what happens when I do that is I'm distributing a y here and I'm distributing a y here. So what I'll have is a negative y squared and minus an x squared y over y, and this whole thing will be over y cubed. And then when I am going to keep going to the next step, I'll have a negative y squared minus, now these y's cancel out and I get minus an x squared, and this is all over y cubed. And that looks actually pretty good in my opinion. I like it. Now, here's the question. Does your answer match my answer? It might not. And here's why. Because the way that you clear your fractions can cause you to end up having things that look slightly differently. You know what I mean? So what I want to say is that there is a chance that your answer, how do I say this? AP College Board may have messed around with your mind. If you look at the multiple choice answers, you may find that they have substituted either for y squared or for x squared. In this case, I would say they would substitute for x squared. And you're like, well, what do you mean? And why would they do that? Well, let's take a look again at the original problem because it's way up there. It says that x squared plus y squared equals 3. And this one actually, like I said, could have been solved for y. It would involve some square roots. It would involve taking, the power rule on a square root. Then you want to have a denominator that has a square root. It's pretty ugly, all right? It's not my favorite one to take the derivative of. But specifically because you can take this x squared plus y squared equals 3 and then minus y squareds from both sides, that's actually a pretty simple process. X squared can be defined as being 3 minus y squared. So in our problem then, they could give you an answer that looks like this: negative y squared minus 3 minus y squared all over y cubed. All right? And why would they do that? Well, it looks to me like what we end up getting is going to be negative y squared minus 3 plus y squared, and this is all over y cubed. They did this because the y squareds cancel out, and my answer will be negative 3 over y cubed. Ta-da! I just thought you'd like to see that.